They ask you to use a tree model for final project or not? Not particular, right? It's a super. So okay, if you really, I think I did mention this one. You really want to produce say nice graphics. With a tree, for the final result tree model, there's a package called Plot. Part of Plot. Okay. Let me see. Yeah, this is a package that allows you to do that. Unfortunately, they don't have vignette here, but there's ways to still look at. They have documents that more. I don't think they might have, but it's not. But for this is very good. This to produce a nice graphic like they already maybe the quick way just to run examples of this sort of all-in-one tree model plot. Okay, this nice graphics rendering is this PRP. I think it stands for plot, RPlot, right? Okay, it's an RPlot plot. Okay. They produce graphics like this. Okay. Just scroll down and here these are some demonstrations. So in this help documentation, you might be able to see that. They also put the whole one in comparison. Something's wrong.
There's some errors.
What did I do? I probably should have done that. Because I used help all. No wonder, because I should start from example. I should use Control A. So just start from the list. That's what we try to do. It's going to affect it out. This is what they have come up with. They try to say it was a nice graphics like this. If you really wanted to present your final model, this is what they have. But they don't have vignette here. One way is that when you install this, it depends on how your computer install the package. For my case, I install a local library. If you probably the reason it happened to me because I didn't install as an administrator for that. So if you install your package, which is reside in the program files, you can go look at for that library folder. But for my case, it's in a documentation. This is like in documentation, go to R. This is like in the Win library. This is very much like your in your case, if you install everything package, this is like the folder. You have this 2.15, so you go there. So you should have this library folder. Okay. That 2.15 is like the library folder, like you see here. Okay. And the package just says what? What is that? Part of plot, right? So they do have some documentation that probably help you with that. Okay. This one. You can see some related RPlot model. It's in that folder, in that RPlot .plot folder under document. I thought they should output this as a vignette, right? They didn't create vignette for that. That's right here. Okay. You can see this right at their top page. They kind of advertise this kind of thing here. So we want to create like nice final result, final presentation and graphics. Go to this one. Okay. So RPlot. This is the package to go. Forgot to mention that. This is the package you look at. And the function to use is PRP.
R part dot plot.
How should I close this? Apparently, I have trouble with this. Okay. So anyway, look into that. You see there are a couple examples there. So I want to take a look at this result. Okay. Anyway, let's get into that. Okay. So it's a new implementation of library folder. In my case, that I have this local library, so that's why it's organized this way. Okay. Otherwise, in your case, you should go to the computer. Where is our computer? How can I find? How come I cannot find this computer? This is Win Library. It's not there. So usually in your C folder and program files, in your installation, you should see this anyway. So either in the documents folder under R and Win Library, or in your installation, you should have this library folder. That's a library folder. Okay. So here, these are actually the default libraries that are already installed. So, anyway, here's an example of that. Okay. Let's turn this off. I don't need this. And this class node, I have that something that this is a. Let me go through this briefly. Applications. And here's some application about clustering method. Okay. About information retrieval. Okay. There's a search engine documents equal cluster documents about the same person. And of course, you want to find a way to logically separate these documents into several clusters. Okay. And in business world, this is about the so-called customer segmentation. Okay. Social network analysis. R has packages about this social network analysis. SNA is a package that do the social network analysis, among others. Okay. And application for training needs, you want to cluster, okay, do clustering in this case. And climate cluster equal region of similar climates, of course, psychology and medicine, attendance and spatial, or temporal distribution of the disease. Okay. You want to divide that into groups. Of course, the number of groups is unknown. Okay. So are the identities of individuals unknown as well. So this is a cluster problem. Okay. Financial risk analysis. Maybe you should just say, well, at the beginning, good credits or bad credits, we have to come by at the beginning. And his own sciences and business segmentation of the customers, individuals for marketing activities. I guess, see, I'm probably not the one to actually talk about this, but just look at this briefly about type of information that the clustering analysis can be applied to. In information retrieval, we have thousands of documents in the electronic archive, and I want to see, for each document, you probably have some keywords that sort of would be used to categorize such documents. Okay. You search over thousands of words categorizing the documents. Okay. And the goal is to cluster documents into groups based on the similarity of content, based on keywords or based on maybe something else, right? Okay. So clustering analysis. So you got to define some kind of similarity or distance measures in that sense. social network analysis, you have thousands of participants or actors in a network. And there's the complex relationships among individuals, among these actors. And the goal is to uncover important groupings of actors into cliques or claims. So, because the groupings is unknown, right? Okay, number of groups is unknown. And for training needs, we have hundreds of workers with training needs involving hundreds of individual topics potentially. And the goal is to organize the topics into logical training modules, courses, and curricula. At the very beginning, this is really unknown. So they still have unknown grouping situation. The goal in such cases is to group the workers according to their common training needs. So you define these training needs, and based on the training needs, how do you characterize the distance between individual and groups? Okay? So similarity measures also. Okay? Financial risk analysis, this group cooperation based on measures of financial risk, isolated cluster containing company of interest, and so on. So anyway, probably a lot of application. I find this interesting, so I put it here. Okay. This is based on articles from that New York Times in that year. And 50 years of U.S. music, 20 attributes, tempo, rhythm, and so on. Okay. And focus on recent hits, 55 hit songs, clusters, new songs. Okay. And like a near cluster center, so you want to class. This is not a classification, okay, right? You still need to know number of groupings. And this is from the application of astronomy. They have this so-called SkyCat. They have catalog of 2 billion sky objects. And the problem is to cluster into similar objects. Galaxies, nearby stars, quasars, etc. Okay. And I guess if you're coming from a biological application, you know this, right? Okay. There's a gene sequencing, right? Okay, about this gene expression in the microarray data. The protein sequencing. The objects are sequences of this 4. How do we call this? These are just abbreviations of 4. These are amino acids, right? Isn't it? Okay. 4 types of amino acids. Anyone can call it. Name this full name. C for what? I couldn't recall that. Okay. Whatever. Doesn't matter. And of course, you want to see a distance between the sequences in sequences. And probably the natural distance to consider is the edit distance, right? Given one sequence from, say, particular biological body and compare it to the other, you want to match them and see how many deletes or insert will translate one into the other. So that would be edit distance. The 2 with a shorter distance means they are more similar, right? So basically, this is the idea. Here, finally, I kind of use this just one slide to talk about some potential issues. It's about, I think, probably particularly in data quantity. Okay? So really, a fast algorithm really needed. Okay? The algorithm we see this hierarchical k-means. This is one way. There are some alternatives. One of this is so-called fast cluster. It's going to be fast. And that fast cluster algorithm was used by SAS. They have this fast cluster or something like that. FASTCLUS. I guess that's the name for that procedure. And of course, those also the data quality and type of data you're dealing with. There are types of data not so easy to define the distant majors, right? Okay. You're probably going to see more like new types of data, and defining the distance is really a question how you define the distance. Okay. Choice of variables and weights and distance metrics, these are all problems. And this algorithm details have something like selection method. Okay. We talk about this different type of linkage method. Which one to choose? There's no definite answer, but I guess you can, if you look at the R implementation, the default linkage is complete linkage. And more or less like you probably, this is the one you want to first try on. Okay. And starting points and convergence of optimality, they are all the problem. How many clusters? Right? That's still another. Okay. Number of clusters, another issue. And stability and assessment could be a problem. How do you assess the goodness of, say, a particular, say, the cut tree? Okay? After you form a cluster, what is the goodness of the model that you form? Okay? So this accessibility, the assessment is really a problem. And stability, there are some method would be very sensitive to small change in data values. So stability could be a problem. Like a single linkage is very sensitive to small change of data values. So we want to take this into consideration and visualization and presentation. That's another thing. So anyway, I kind of we just this is only intended to be introduction, so not get into very detail of that. Did I finish that example last time? Not done yet, right?
No, didn't finish.
I didn't finish it. 16, right? Yes. Assuming we have this protein data already read. Where did I stop last time? I think we stopped at this position. Actually, we done all the hierarchical clustering last time. So have this Agnes, okay, Agnes method here. I guess we need to require cluster. And this is last time. This is last one we said last time. Okay. Here, this is banner of Agnes. This is another way to present the dendrogram. Okay. Actually, I like dendrogram better. This is way to display the result. Okay. So Agnes is actually this agglomerative nestings. That's this agglomerative algorithm, hierarchical algorithm, implemented in this package cluster. Now let's look at partitioning method here. Okay. First, look at k-mean clustering. Suppose that instead of indicating the starting centers, that we use the random starts. Okay, so here, of course, by means random start, we need a starting seeds, right? This is random number generator. So write the starting seeds here and see the result. Okay? This is k-mean cluster. And it's going to, when you run this k-mean clustering, the model is going to give you the centroid or the cluster means of these 6 centers. Here we actually specify there are 6 centers. So remember, this is actually one of the drawbacks of K-mean cluster. You have to decide the value of K first before you do that. But usual recommendation of K-mean cluster is you not only try say 6, try some of them, and there are some pseudo F tests allow you to test whether one is better than the other. So anyway, let's say we stay with the 6 centers. So we are trying to form 6 clusters here. Okay? And then here we have random start because we use the set random thing. We simply just say 6 centers for that. Okay? So R will randomly select 6 observations from your data set. And those observations will form initial center, right? And gradually updating that with the result. Remember we talked about that. First, each observation will be within each cluster. We test whether it's closest to its own center or to some other center. If it is actually closer to the neighboring cluster, then you will assign the object to that. Okay? And this process is done iteratively until converged. And the result here, basically, these are the final cluster means. The center, according to these measurements that we have this. Of course, this is a scale result. Scale this protein, right? So here, this is center and scale result. Okay. And at the end of that, the cluster form are this. So basically, these are the clustering vectors identifying the membership of this. Okay. So here, there are 6 groups here. This is that grades belong to group number 1, cluster number 1, and so actually the first one, Grace and Italy, they come from the same. According to this K-mean cluster, their cluster has the same cluster, okay, same group. And so here, this is the numerical presentation, the result, okay, and tells you about within cluster sum of squares by cluster, okay, will be given by this. And between cluster sum of square versus total sum of square is 72.4%. Likely, if possible, you want this as high as possible, isn't it? Okay. So here, it also reports this result, okay? And these are available components in this data. Well, this is final data. Final model, where is it? Cluster. Here, the final clustering model is PRKN. Okay? Contain this object. Of course, you can take this information and produce a graphical result. That's what I did. The next command here, I run as pairs. Of course, probably this is. Of course, by default, you can run pairs for all these input variables, but that would be too many variables. So just a view about this result. I only take the first 4 variables and see the result. This may not be the best result. You might want to look at this way too. Is there a way to judge which variable is more important than we probably want to produce scalar plot matrix for those variables? Okay. I only picked the first 4 variables to display these pairs. Okay. So apparently, according to this, there are 6 clusters. Okay. According to like this one, probably this cluster is sort of clearer than others, right? Except for this point. Okay? So here there are one cluster here. I use a different color to represent each cluster. Okay? And cluster package also has something called partition around methods. I think I mentioned about what definition methods. Methods is actually an actual observation. Unlike centroid is the average coordinates. Okay, it's simply the average coordinates of the object, right? The Meadow is one of the objects in the cluster, okay, which is most similar to all other objects. Okay. Basically, within a cluster, you can take for any object in the cluster, you can calculate the average distance, right, of this object to other object, and the one that with the smallest average distance, okay, with as a method scheme, so that's called method scheme. And partition around method is basically just with that idea, okay. Did I mention about this function last time? Daisy. Daisy, this is similar to DIST, distance. This is in the standard distribution. I don't know why they call it like this kind of different name. But that's a measurement, that's distance measurement. Okay. The idea of this Daisy is that you can also, by default, it's a Euclidean distance, and you have the choice of Manhattan distance. You also have a choice of Gower's distance. We talked about Gower's distance before. The standard R distribution function, DIST, take care of like Euclidean distance, Manhattans along with others, but it does not take care of the Gower's distance. Okay. Well, here in this page, I simply just use Daisy's anyway. So without doing anything, I say Daisy protein minus 10 basic. This is just to produce. I think we probably also need to say center. I think standardized. I think I forgot about that. Otherwise, these measures are very different. They have an argument called standard right here, right? Standard. Forgot to do that. So here we need to standardize this. Now, of course, here, strangely, I think I remember the reason why I didn't put standardization. I used original measurements, arguing that probably these measurements are sort of alike. Okay. If you use a standard, it will not get back to your sort of this regional clusterings of the geographical location. So if you try this out, and then let's try this one, and run the summary. Okay. So here, these are the partition around Medoid result. Return with this. There are 6 centers. Of course, here we try to decide with the 6 clusters as well. Now, of course, if this result is not really easy to understand, you can try to plot, okay, the information from this. One of this is so-called this silhouette plot, okay, information. Okay, produce silhouette plot. Okay. I'm going to explain this a little bit. Okay. But let me run this plot right here. I have to leave some room for that. So this one, let's look at the result. Oh, this is not silhouette plot. But did I plot this? Oh, right here. Okay, so this cluster plot, I first have this cluster plot. Okay. It's quite a mess here. It's really hard to see that. Okay, cluster plot basically this is in a sense they project this high dimension into 2 dimension only. So in a sense, this is like you project to the transport components, right, and see the clusterings of the result. Okay. Does this help? Basically, use this ellipse to circle like different clusters, and the pink line sort of give a concept about the distance between clusters. Okay. Not really helpful in that, but let's look at this. Okay. Actually, what I need is this plot, okay? Not that one. This is so-called silhouette plot. Okay. Actually, you can see that from this plot, there are 6 clusters, right? You can see that. Okay. So basically 6 clusters: 1, 2, 3, 4, 5, 6. And the memberships are so those from that individuals who plotted. So we know that membership. Probably I should downsize the font to that, so make it easier to understand. Basically, this is so-called silhouette plot. They plot this major so-called silhouette, okay? And silhouette computed is something like this. In a sense, it's kind of interesting. Okay. First, you calculate something, some measurement, so SI for any. Let me try to explain this. AI is the average distance. Okay. Average distance from that object. So just like that. This is you calculate the average distance from that particular object, okay, to all other objects within the same cluster where I is located. Okay, so that's first. And BI, okay, this is average. Average distance from. Sorry for the terrible handwriting. Yeah. Of course, here we have to define what is the nearest neighboring clusters. So basically, for any object, you are able to calculate the distance, the average distance from that object to all objects within same cluster. You can also calculate average distance from this object to other clusters, right? And whichever cluster having the minimum average from this object to that cluster is so-called the neighboring cluster. Does that make sense? Okay. So you're sort of having this. Okay. And then here, suppose we single a particular object here, and then here I have another cluster here, okay, with this point, and then let me put one that's closest one. So we have ideal neighboring the clusters. Okay. So AI is the average distance of this point to all other objects within the cluster, and BI is the distance, average distance from this to all 3. Of course, you can calculate average distance from this point to this cluster and from this point to this cluster. Okay? And the neighboring cluster is one with the shortest average distance. So basically, you have this measurement. Okay? And this silhouette basically is this measurement. Of course, the idea is that we want this number to be as large as possible, right? So usually this number is in between +1 and -1. Okay. +1 is achieved, literally speaking, if AI. Do I have this right? SI is, I think it's distance or something. Say if AI distance. Actually, something is wrong here. Well, anyway, the idea is that if that silhouette achieves the maximum one, it means that basically that object is supposed to tightly clustered to the correct place. Okay, the negative one means it's really bad. I think I have this reverse, right? Isn't it? Because if we want the cluster correctly positioned in its cluster, we want AI to be near 0. So that BI will be greater than AI, right? It's all reverse. I don't know, something is wrong. I'm going to write as a short slides for this. Forgot about that. Okay. But actually, no matter what, you want this silhouette measure to be as high as possible. Okay? So like this one, for this cluster means that this is tightly clustered because most of them, or at least the 2 countries, right? We have larger silhouettes, right, for this result. And this cluster is kind of loosely clustered together because they have small silhouette measures. Okay. So you look at the help of that, maybe they have it. I think I have this measurement first. Let me check on that and see. When I write this out, I feel that something is wrong. This is like reverse, isn't it? Okay. Maybe that's the case. It's BI minus AI, I think. Yeah. No wonder this is not right. There's something is wrong here. Yeah. So when AI is much less than BI, so let's say probably near 0, right? Compared to that. So here basically BI dominates is BI over BI, so 1. So it means that that object is closest to all the objects within the same cluster. That makes sense, right? Okay. Otherwise, that will be the other one. We achieve -1. I'm going to double check and make sure this is correct. Okay. But anyway, that's the idea. Okay. So here, this so-called silhouette plots basically give you the visual idea about how tightly clustered the object within each cluster. Okay? So in this case, this means this is nicely clustered. Probably not so good here, right? Every silhouette width is only 0.28. That's probably not a good. That's not a good result. Should we try this with the one without standardization? Let's try this one. See what happens. Let me run this, and I guess I need to run this again. Not much improvement. I thought it's going to get better results. It's not. Of course, it makes more sense if we should standardize, right? Because of these measurements are somewhat not compatible. Some of these measurements are proteins and some from eggs, some from the animals, some from like plants, right? So probably should standardize them. Okay? So maybe I should retain this to the standardization. Here I just mentioned briefly. This is a way that R do that. Suppose, of course, you don't have to do this plus. You can assign that margin directly. R allows you to call this parameter to set a new margin like this, and at the same time, it will save the old margin. Okay? So this is kind of weird. Okay? suppose original is 5442. This is more likely the 4 margin, okay? And that 5442 will be saved in all part, but the new margin is set to like, in this case, 5742. I leave more room on the right hand side, so on the left hand side, so we can plot this text string here. That's why I need to do that, okay? And so save there. So one way to resume to original parameters, so that your subsequent plotting will look right. Otherwise, you need too much room in the subsequent plots. So one way to do that is using this, resuming this parameters by running that mouse or plot. I guess you do help. You do help on PAR. You see how to use this. Now here, this is the next one is kind of twist. You can use unsupervised learning technique, okay? And then try to come out with the clustering. I mean, well, of course you do clustering. Unsupervised means clustering, but then you compare the result with sort of the result that we're supposed to do with supervised learning, because in this case in iris data the group identities are known, right? So we know all the what type of plans that we have in our data set. But we first treat as if this is unsupervised learning, and then see what happened to the cluster, okay? The best result we got. Okay? So here, let's say we run this, require random forest and SETC, and run random forest. Okay. The way we run it, here random forest run with X only. I didn't put information about Y, so this is an unsupervised learning version of the random forest, right? Can you see that? Okay. Normally, if you run this random forest with supervised learning, you need information for Y, right? The class identity here. We didn't provide with that. Okay. So this is unsupervised learning. And let's say we run this as a computer language by changing this. So remember when we talk about random forest, this model fit will give this proximity measure, right? Proximity base is measure of similarity, right? Okay. The theory says that if you of course you can. Let me erase that. For this proximity measurement here, this where was that? Here, this proximity result of this data set. This is huge. This is a huge data set, of course, right? 22 by 25 or 25 by 25. This is we had run this already. I thought we run this random forest already. We still run with 14 data. Okay. So here this proximity, you can actually see this. This is the matrix of similarity. Okay? The matrix of similarity, I call it that. And you run an eigenvalue on that. Only. Forgot about this. Only values. Sorry. Sometimes it's not so easy to remember this. Okay. It's only value. Okay. Otherwise, just say only. Okay, the eigenvalues of this proximity matrix are all positive. So actually, this tells you this similarity matrix is positive definite. See all the eigenvalues. The smallest one is this, right? They are all positive eigenvalues. Now, if similarity matrix is a positive definite, then you can define through a similarity matrix distance matrix. Otherwise, you cannot do that. Okay? And the definition of that, actually, I didn't make this check. Probably I should. Let me put this here. Okay. We should check this eigenvalue right here after this. So make sure you can do that. So we run this eigenvalue analysis on just looking at eigenvalues. Yeah, all eigenvalues are positive definite. Then you can define a distance matrix through these eigenvalues, through this proximity matrix. Okay, or similarity matrix by doing this. Okay, here this is square root of 2 times 1 minus similarity. If similarity matrix is positive definite, like the one we see here, all eigenvalues are positive definite. And you run this 1 minus this times 2, taking the square root. Okay. To get a distance matrix. Okay. So that would be the result. And then you force that, actually the result, because when you do this, the result is only a matrix, right? It's not a distance type, so you force the distance. That's why you can do this hierarchical clustering with that. Okay. So I use that. Okay, 1 minus a similarity matrix right here. Okay. And taking the square root. Of course, you can only do that if similarity matrix is positive definite. So that's why we actually need to check this eigenvalue. Okay. Now let's run this hierarchical clustering. Here, this is the result from this complete linkage. Okay, and let's say, suppose we want to cut this into six clusters. Okay, we run this plain reg hierarchical class. With this, we send this result. Is this consistent with the result we see? Not exactly, right? Okay. Of course, you can use this as as classification. You compare this with the actual geographical location. Okay. This is a way of classifying. This is actually this is the one I'm going to try to talk about, not that one. Okay. So using clustering algorithm to do that, we run this ECNIS. This agglomerate clustering, and we have this result. Okay. This spinner plot is not really easy to see because there are 150 observations. Okay. So the one that's sticking out too much, this is not really good. So you want to try to cut in some moderate size. Okay. And you cut this tree too low, you end up with too many clusters. Okay. So it's somewhere in between. Okay. But not too far, not to the far end on the right hand side. Of course, you also need to look at. Well, it's hard to see, right? Because we have 150 observations, so that's why they all overlap. But looks like you can actually see. If you try to look at this, apparently we can do something like 3 clusters, right? If you cut on a moderate size, like somewhere from here to this one, here this part form a cluster, right? And then you have cluster right here. This is another cluster, and here another cluster. Let's see that. See what happens to this. Okay. So suppose you do 3 clusters, okay. You can actually see this result. Suppose I cut the tree into 3 clusters. Now here, this is the actual identities of the iris plants, right? And now here I use this clustering result by the cut tree, that dendrogram. Cut into 3 clusters from that result. Okay. You can see that this clustering can pretty correctly identify all Setosa and versicolor plants. Okay, of course not this one. Virginica, there are 14 of them in this class, right? But this is not really bad, right? Okay. So here, this is a trace of using this unsupervised learning. You can turn that into like one type of clustering algorithm. Of course, the interpretation is not so easy, but you can actually argue it's based on distance that is within certain limits, from the 3 clusters, right? And you can see in the scalar plot matrix the result of this. Looks like if you look at the clusters, like most of them, you kind of interpret like how can I choose this? Setosa, okay, great. Choose these 3 colors. Okay. So here, it's this Virginica, the green color sort of go into the sort of heart of the other cluster, more or less. Okay. Look at this cluster, this scalar plot matrix. Okay. If you look at in terms of like similarity measures, okay, it's how similarity measure this result. Okay. So here, all this versicolor, any object within the versicolor, they are more similar to, on average, to other object within that than on the average to the other one, right? So that's why they were all correctly clustered, but not the other one. So maybe some of this point, like in this Virginia, just go too far into that. Here, this is a kind of interesting twist of using unsupervised learning to do clustering.
Yes.
We are going home for Thanksgiving. Should I continue? Probably not today.
You want to talk about the case file?
Huh?
Study case file.
Case study file.
Yeah.
Oh, but also the final exam, right? I mean the final project. As originally, I kind of designed this course as hopefully in the final project, you can work on project and also present the result. I'm trying to find out if it is possible to do that, to have presentation in the final exam week. Probably a bad idea.
Yeah.
See, I really want that happen, but so how is your schedule? Is it? Do you think it's going to happen? Or what is the due date I said that for the
13th.
13? That's Wednesday, Thursday. That would be too late for. Well, how about we skip that anyway? So just turn it as a final project, okay? Yeah, I thought originally I can schedule that, and then after looking at this, probably not possible.
So we take on study 5 or 5?
No, they are 2 separate things here. You have final project, and then there's a case study file.
Yeah.
You want to look at. What kind of question do you have?
Study 5 of the date. The date of the week. Simply with the date.
They have date. They have date column.
Yeah, it's
that,
not data, it's date. How to read the
Let's
date.
see if we have that. Where is the date measurement? This
What's the
one, huh?
color of the river?
They have this dy. This probably won't work if you. This is really bad. Get that. Let's see.
We didn't date with SAS.
No. SAS usually still have the tree with like a character variables. This is all character. Let's see if I can do it this way. This the first one is supposed to be date, right?
Yeah.
And month.
Percent D slash
Must
percent
be they use M. They use M.
M slash
And
percent
Y. It's lowercase.
Y.
Looks okay. Isn't it? So maybe for your question, let's see, maybe I need to change this. I didn't particularly do that. Let's see, we will do this. Copy that and see if we can run this. Okay. So, do I ask you to only work on the complete cases, right? 1 or 2, right? Is it?
Yes.
Okay. Let's just look at that. See. Huh? How come we have nothing here? That's weird. You only subset the complete cases. You want it. That looks okay. It's 1 or 2, right? And then we scale it. We have a problem with the scale. Where is this scale come in? Hmm? Oh, 1 or 2 get scale. That's right. Tree of the I didn't assign any names to that. Let's just use this name. How about that? Okay. So then we have that, and is it the first variable that you have this non-numeric date? The first one, right? Oops. No, not the first column.
No. What's the color not include the date? No.
I guess one thing you can do is after reading this, use a substring. Yeah, use a substring because basically they all start with D dash there, right? SUBSTR. Let's see. Yeah. What did I do here? I thought I had read this. I had read this columns in there. get that date, you can use like, for example, this is get from the first column, okay? Substring of, suppose this is
1, 2.
column 1, right? Is it column 1? So how come I read, we have the whole bunch of missing variable there?
It's not. It didn't read this first column, I think.
Didn't read the first column?
No.
No, I don't think so.
Yeah, but it's not here. I will check.
Let me, I use the first, okay. Yeah, see, I say row.names equal 1. That's right. This is really important. This is the days. Do you want to use this date information in the analysis? I thought this is only identification.
Don't need that, right?
I guess you don't need that. Well, if you actually want to change this into this one, you can use.
Row names 1 and 2.
These are the first 10 numbers that you have in there, right?
Oh.
These are row names, right? Actually, it's only used for ID. If you want to put this in the date, I think there's a way to do that. Okay. Okay. Let's start at doesn't make any difference. Okay. This will extract that D dash there, right? And of course, these are still text string. If you want to make this into date, you can do this. That's the one we've seen there. When did I do that? Actually, you don't need to change put that into. This is only for the ID for the. It's only ID for the cases. Okay.
Well, you don't need it.
Yeah, actually, you don't need to do that. We need to do that. This is just to convert that into date. But you don't need to do this. This will force that into date type. Okay. For example, we can pass that to plus 10 days with that. That will be changing. Okay. You can operate some date, but you don't need to. Okay. So I thought you really need the date information. Date, in this case, date is only just for identification observations.
Real quick, what's the plus 10 do?
Huh?
What
No,
is
I
that?
just add 10 days to each one of them.
Oh, okay.
Just say, when you actually, originally when you do that, this is only text string. But when you translate that into date object, these are actually integers. That's just printed that way. Okay, let me stop. Okay. What did I promise you? I need to change what, check on that formula, right? And what else? I need to check. Okay. I need to prepare the examples of this PRP.
So we have to choose profile project and this.
Yeah.
Okay.
Yeah. So case study number 5, and then final project. Okay. So we still have how many weeks to go?
2 plus finals.
2 plus final. Okay, about 3 weeks, right?
Yeah.